Tomasz Maszczyk.
Thank you. So what I'm going to talk about is one of names given to some part of scientific endeavor, which started as ironic or even derogatory, and it turned out to be very accurate and to the point. You can compare this abstract nonsense phrase with other phrases known in science, like black holes or a Big Bang. So both these notions in physics started in the same way as some ironic commentary to some scientific programs. And at the end of the day, it turned out that it is a very, very good way of speaking about things which otherwise could be expressed in other terms. So abstract nonsense today is understood as some description of some thinking, some kind of thinking in mathematics, especially, which uses the notion of category. So categories is a very old notion, known from times of Aristotle, but the use of categories in strict mathematical thinking is quite fresh. I'm not going to speak about history. You will see what is the kind of mathematics which needs this language, and I hope you will like it. I cannot move my. Maybe I will. I have to do this. Yes, 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 I will. But you can also just. Okay, okay. So what are categories in mathematics? Essentially, it's a kind of algebraic structure consisting of a collection of so-called objects. This collection is denoted by ob of C, if C is the name of this category. For every two objects, X and Y, we have a collection, T of XY, of so-called morphisms, denoted as arrows. Okay. So what are rules? For every two morphisms, we have defined a composite of them, denoted in a way as we usually use to denote the composition of functions. For every object X, we have also a distinguished morphism, which is called the identity related to this object. And they satisfy some constraints. First, it's called associativity, which means that we can compose this morphism according to the rule of moving parentheses, as we know from arithmetic. Okay? This composition to be defined demands the source of one arrow to be the target of another one. And then, if we have a triple of such composable pairs, we can form two kinds of compositions. We can compose second and the third, and next we can compose it with the first one, and this will be the same as the composition of the first two composed next with the third one. And this associativity of composition is accompanied with the property of unitality, which means that if we compose every morphism with a corresponding composable identity, then we obtain this morphism again. So there are many examples of such structures in mathematics. First of all, the category of sets, denoted by set. Objects of this category are sets, and morphisms are functions. Second example is the category of topological spaces, whose objects are simply topological spaces, and morphisms are continuous maps. Everybody knows that these rules for composing of such maps hold. Third is strictly related to the second one, is the category of topological spaces, but instead of taking continuous maps between them, we can consider homotopy classes of continuous maps. And it turns out that the composition of these classes is also well defined and satisfies all axioms of category. Next, if you learn analysis, you encounter the category of manifolds. Objects of this category are both manifolds of class C infinity, for instance, and morphisms are smooth C infinity maps. Next example comes with the theory of analytic functions. They live on objects which are called analytic spaces, and morphisms between these analytic spaces are so-called C-analytic morphisms. Okay? Very close situation we have in pure algebra when we can speak about rings instead of algebras of holomorphic functions. And then we can globalize the notion of space in this language to the notion of so-called scheme. I'm not going to explain in detail what scheme is. You should think about schemes as some algebraic version of an analytic space. Okay? So if we fix a field K, then we have the category of schemes over the field K. And morphisms are appropriately defined morphisms of this object. So this example is the basic environment of algebraic geometry. There are many structures related to order. There are categories of pre-order sets, the category of partially order sets, whose morphisms are monotone functions. There is also very important category in mathematics, especially in algebraic topology, which is called the simplex category. Objects of the simplex category are non-empty ordinals.
Sorry, I have a question. So do you consider all possible non-empty ordinals or only those corresponding to natural numbers?
Yeah, you can restrict yourself to.
So this is a small category, yes, finite.
Yeah. So this algebraic topology usually uses finite order.
Mm-hmm. So it is a small category, yes.
But this restriction is not a understanding. So morphisms are order-preserving maps. Okay. Close to these order structures, we have some kind of algebraic structures related to them, like lattices, Boolean algebras or hating algebras. Since they are kind of algebraic structures, morphisms between these objects of these categories are homomorphisms. These are mappings between sets equipped with these operations, algebraic operations, which are compatible with this structure. Okay. More algebraic examples. First of all, the category of monoids, category of groups, category of algebraic groups with homomorphisms between objects also are examples of categories. Similarly, the category of rings, the category of fields with homomorphisms as morphisms provides another bunch of examples. Strictly related with these examples are the categories of modules for a given ring R, or category of vector spaces over a fixed field K, with morphisms which are linear maps, which are in appropriate sense R linear or K linear. Okay, but also in the theory of proofs, we have an example. If T is any deductive system, then we can regard formula of this system as objects, and then morphisms could be taken as proofs.
Sorry, so may I have a question to this 13 example? So what is the status of the axioms in this approach?
They hold.
Yes.
These are examples categories.
But meaning formulas are objects, yes, so proofs are morphism, but axioms are true, but they do not require a proof. So
and usually we do. Okay.
So maybe to express it in other words, can you somehow name what is the role of the axioms in terms of category theory in this example?
If you have a formula,
it is like something
then,
like initial object, for example. That
no.
Please use a microphone when speaking.
Yes. Yeah, yeah. I don't.
The initial object of a deductive system is a set of axioms of this deductive.
Yes, and inference rules allow us to perform proofs, which can be composed.
So probably inference rules are elementary arrows and proofs are compositions of these,
Yes.
and then you can compose proofs.
okay, thank you.
And the last example is a category of any computational model of computation. Okay, when objects are data types and morphisms are programs, and these two examples are strictly related.
So sorry, once again, the question this time for this 14th example. So how to explain in the language of category theory when the program it's trapped in the loop, never holds. So is it somehow expressible in this categorical?
Because loops are loops. There are morphisms which are loops.
But what does it mean? It means that the domain and codomain coincide, and that's all, or something more?
Yes.
Okay.
Maybe it's
Okay,
not
thank you.
a model of effective computation, but it's still running.
So an identity is
Sorry?
an identity is one particular example of this phenomenon.
Yes.
Okay.
Okay, so in this way, we run through all mathematics, and everywhere we see this fundamental structure. It's called category. Okay. So paraphrasing Le bourgeois gentilhomme of Molière. My faith, for more than 40 years, I have been speaking categories while knowing nothing of it. And I am the most obliged person in the world to you for telling me so. Okay. But if there are so many categories, one could ask whether mathematics is a single subject or it is a bunch of unrelated, locally consistent pieces, which can be rephrased as the following question. Is mathematics a natural born organism or an artificially made kind of Frankenstein monster? So first of all, we have to recognize naturality. What is naturality? So let's investigate. What is the test of naturality? So it starts with some addition to the plain notion of category, because different categories can be related by arrows, which are called functors. It's an application which sends objects to objects, and for every pair of objects in the domain of this functor, sends morphism between x and y into morphism in the category D between their images under this functor F. And then, of course, there must be some restrictions for the rules of this association, of this application. So first of all, this must be compatible with composition. And second, it must be compatible with units. What is good about this point of view? In a sense, meta-categorical view on the bunch of all possible categories in mathematics. The first good thing is that categories can be regarded as objects of some category whose functors are morphisms.
Sorry,
in this category.
Quick question. Do you need those categories to be small?
No.
Okay.
But there is one step further, because these functors also can be related by some higher morphisms, which are called natural transformations. So the word naturality appears first in this context. So what is the naturality test? The naturality test is checking whether a given bunch of generalized or higher morphism between functors satisfy the commutativity of this complicated square, in which we have images of the functor f related by the corresponding image of the morphism f between them. We have the same for the functor g below, and vertically we have some morphisms, some bunch of morphisms that indexed by objects in the category C, which together form this natural transformation. And the demand is that this square must commute, which means that the composition of phi y with f of f is the same as the composition of g of f composed with phi x. If this bunch of components of this double arrow phi satisfy this commutativity, then we say that it's a natural transformation. Although mathematics is not a natural science, it looks and behaves like one. Okay? However, it is more powerful. I hope you recognize this picture. If not, okay. So this is a replicant, Roy Betty, okay, from the movie Blade Runner, saying that I've seen things you people wouldn't believe. Okay? And the secret power of mathematics is abstraction, without which people are keen to classify things based on completely bogus analogy. So first example comes from Herman Melville from the book Moby Dick, okay, where a definition of a whale is given. So to him, the whale is a spouting fish with a horizontal tail. Okay? Another anecdotic bogus analogy or definition comes from the lives of the eminent philosophers of Diogenes Laertius. So let me read it. When Plato gave the tongue-in-cheek definition of man as featherless biped, Diogenes plucked a chicken and brought it into Plato's academy, saying, "Behold, I brought you a man." And so the academy added with broad flat nails to the definition. So, as you recognize, there is some fallacy in all this classification and definitions, which today is called the category fallacy. Okay? So, how to do properly this classification and defining things among others? So, the idea is to group the objects as they behave in a given category. So first we have to fix the category. And then we are comparing them through the functor which takes values in the category of sets, or locally small category, so-called. And it is of the following form. We are fixing the object X, and we consider all possible morphisms from all other objects in this category. Okay? So this set, or this functor, measures how X interacts with all other objects in this category. And if two objects interact in the same way, we decide to identify them. But we have to remember how they are compared, how they are identified. So the first step is easy to grasp, because it is very intuitive to make things which are equivalent from some point of view, to regard them to be equal. But the second step, keeping track about the way of comparison between these objects, is quite tricky. Okay. For instance, objects of the category of sets are classified by cardinality. Okay. Objects of vector spaces are classified by their dimension. So, but how classify more complicated objects, non-linear, not more complicated from the point of view that, from this point of view, that they require a more complicated category. For instance, oriented closed surface. Intuitively, it's quite easy, because if we look at such a surface, we see that they differ by the number of holes. But sometimes the position of these holes can be different, but these surfaces can be obtained one from another by some continuous deformation. Okay? So you see, for instance, 3 examples with 3 holes, and 1 example with 1 hole, and 1 example with 2 holes. So it's easy to say, but how to define strictly, rigorously this number, not looking at the surface. So the question is, what is this number G? it turns out that it's a half of a dimension of some vector space denoted by H1X Q, which is a vector space of a rational numbers Q, associated with a surface. And the rules of this association are that this is a functor. Okay? Which means, for instance, that for any continuous map between surfaces, X and Y, we have a linear map between these associated vector spaces, which is compatible with composition and identity. Yes?
So, as I understand it, we associate to X this vector space H1XQ, and to the arrow, the arrow associated with F is this linear mapping
Yes.
between H1XQ
Yes.
and H1YQ. Okay.
So in a sense, you could write that this map, this linear map, is of the form H1 F, Q. Okay. So this is a quite powerful way to construct so-called invariants, which could be used to distinguish objects. And even if in more complicated categories, invariants are not enough to classify objects up to isomorphism, they are always the first step toward this path. Okay. Sometimes it is quite difficult. In particular, one could dream about invariants which fully or completely characterize our objects of our complicated category. So we saw that this number of holes, this number G, which is called genus, is a complete invariant of an oriented closed surface. Okay? But it's a very rare situation that we have a very simple numerical or algebraic invariant fully characterizing objects of some complicated category. Sometimes we have the whole bunch of invariants, among which some of them are of this simple numerical or algebraic nature, but still there are some other invariants which are more complicated, and they have a nature of continuous invariants, which we call moduli. So let me show you an example. Let sub W be the category of linear embeddings of vector spaces into a fixed vector space W. Okay? So take this as objects, and morphisms between these objects, they are commutative triangles as depicted below. Okay? F being an isomorphism, if we want to identify these embeddings up to isomorphism, fixes the dimension of this space, V, let's say equal to K. But still there is a whole scheme of generalized space, algebraic nature. In fact, it's a variety, which is denoted by GKW, and it's called a Grassmannian, which is of positive dimension K times n minus K, when K is the dimension of V, of the subspace, and n is the dimension of the ambient space. And this quite big space parameterizes in a continuous way k-dimensional linear subspaces of W. Okay? So this makes this simple classification project, even of such a simple situation, quite complicated. But this can be made easier if we understand that there is a functor behind this construction. This is called the moduli functor. And it makes sense in much more bigger generality. For any category C, we can consider a functor from the category C with arrows made opposite to the category of set associated with every object of this category T. Again, this set of all morphisms in the category C from the object T to the object X. We can rewrite this application HX, leaving this slot for X blank. And then this defines another functor from the category C itself to the category of functors from C up to set. Such functors are sometimes called presheaves, if you like. Fancy terminology. Okay. So on objects, it acts as follows. If we have an object X, we associate with this functor HX described above. And on morphism, it acts in the following way. If we have a morphism from X to Y, called F, then this functor associates with this the transformation HF between these two functors, HX and HY. And this is given by a very simple recipe of post-composing this E with this F, or pre-composing with this F. Okay? And this is very important functor, which is called the Yoneda functor. This is important because of the following lemma due to Yoneda, saying that for any object X of the category C and any functor F, capital F, from the category C with arrows reversed to the category of set, there is a bijection, which is natural in X, between set of natural transformation between the functor Hx and the given functor F, and the set of, which is the value of this functor F evaluated at the object X. As a consequence of this lemma, we have that this functor H blank from the category C to the category of presheaves on this category C is fully faithful, which means that this functor on morphisms is bijective, because fullness means surjectivity and faithfulness means injectivity on morphism. In particular, you can regard this category C as a full subcategory of the category of functors from the category C with arrows reversed to the category of set. So full subcategory means that we embed this category of C to the category of presheaves in such a way that morphisms in this ambient category reconstruct the original morphism in this category. And then the following problem arises, the problem of representability. We say that a functor or presheaf is representable if there exists an object X and a natural isomorphism between this functor and this functor Hx of morphisms from arbitrary object of this category to a given object X. If such an isomorphism, natural isomorphism exists, we say that this object X represents this functor F or this presheaf F. Okay. How to use this point of view to clarify the moduli problem?
Excuse me, can you please give us an example of a functor that represents a object, a slight value?
I'm going to do this.
Okay, thank you.
Maybe in 30 seconds. Because such representing functor will arise from the moduli problem. So what is the moduli problem? So let's fix some category. So for the purpose of this illustration, it will be the category of schemes over the field K from algebraic geometry. Okay. So if we have a presheaf on this category, we could think about the representability of this presheaf by some object as well. Okay. So take the functor associated with every scheme T, the family over T of some object you are going to classify. Okay. And classify up to isomorph. So by family, I mean that I have some scheme X. We have a morphism of scheme to some scheme T. And the word family means that fibers of this map, okay, are these things you want to classify in this family. Okay. How to make it a functor? If we have a morphism from another base of this family, from T prime, then we have the induced morphism along this functor F, which reverses the orientation, the direction of this arrow. It is defined by something which is called the pullback along this morphism from T prime to T, which means that new family obtained as a result of this pullback, which I denoted by X prime over T prime, fits into the following diagram. It's a square where you have two vertical families, X over T and X prime over T prime, satisfying some condition, which is denoted inside of this square by this little square. This universal property is follows. In blue, you have another vertex of another diagram, commutative diagram. For every such blue part of this diagram, there exists a unique morphism of families from this family X tilde to this X prime. Okay. Sometimes it's called Cartesian property or the pullback property.
Excuse me, is this somehow connected to covering spaces in topology?
Not so much.
Okay, thank you.
But of course, you can think about every covering space as some kind of family of set parameterized by some base. Okay? The same about more complicated bundles when the fiber is not discrete.
Maybe the connection is that in this category in general of vector bundles, pullback is a very natural construction. So maybe this somehow answers your question. Since
so we have the following definition. If F is representable by a scheme M, then we thinking about this problem as a kind of classification problem, we say that this representing object M is a defined moduli space for the moduli problem equivalent to the choice of this functor F. For instance, coming back to our example, let us consider now the functor F, the presheaf on the category of schemes over a field K, to the category set, which associates with every base scheme T the set of isoclasses of rank K vector subbundles of the trivial vector bundle of the form the base with the Cartesian product with the vector space W. Okay? And then we have a theorem. the functor f is representable by this Grassmannian. Okay, so this is your example. So the solution to this quite abstract problem is this intuitively simple algebraic variety of parametrizing k-dimensional subspaces of a vector space W. In other words, this Grassmannian is a fine moduli space for the modular problem F. Let me remark that in general, over the fine moduli space, there is always something which is called a universal family. If you have this functor defining the modular problem, this functor F of isoclasses of families, then there is also a distinguished element of the values of the functor Hm applied to this representing object itself M, which is identical. So this distinguished element distinguishes also a universal family over this moduli space. In our case, in our example of the Grassmannian, it can be easily described. By the way. So first of all, what is universality? Universality means that every other family X over T is a pullback of this universal one along something which could be regarded as a classifying map, which is a map from the base of this family to this base of the universal family, which means that we have such pullback or a Cartesian diagram between these two vertical families. For instance, over Grassmannian, the universal rank K vector subbundle of the Grassmannian cross W is nothing but the so-called tautological vector bundle, which can be very easily described as a bundle whose fiber over a given subspace V of this ambient space W is V itself. Okay? So this motivates the name tautological. The definition of this virtue. Okay? These ideas and many more stemming from categorical thinking today organize all mathematics and some areas beyond mathematics when mathematics is used. For instance, today we have some tenets of computational trinity, okay? Which is a circle consisting of three subjects: computation, spaces in general sense, and logic. When these places in this diagram could be filled with some concrete content. Computation, it's about computation and programming languages. Okay? By spaces, we mean category and topos theory. Toposes are some categories which would be regarded as some environments for doing mathematics. And it turns out that besides the topos of set, which is the classical environment for doing the classical mathematics, we could think also about environments of some exotic mathematics. For instance, it was a way to prove that the axiom of choice is independent from other axioms. We can create models which are not theoretical to test some axioms of some defining some theories. Okay? On the side of logic, this triality have this content about some kind of logic which was present in fact on the list of categories. When I was talking about Boolean algebras, so everybody knows that Boolean algebras is the algebraic structure of propositional classical calculus. Okay? if you change your environment from classical, theoretical foundation of mathematics to some exotic toposes, it turns out that every topos has some internal logic. And there is some counterpart of Boolean algebra there. And they are hating algebra. So hating algebras were on the list. So the conclusion would be like this. If you want to understand deeper and broader, use rather categories and ranks. If you recognize it, move. Thank you.
Thank you very much. Okay, any further questions?
Can you please write a concrete example, like in concrete object, in concrete category, in case of this vector bundles and Grassmannians? I'd like to see like
What's concrete?
like
You have a
taking-
concrete vector space W,
Okay, yeah.
and you are considering all possible embeddings of vector spaces
Mhm.
in this given vector space.
Oh, okay.
So W is fixed,
Yeah,
and you
but
have a very big category of all possible vector spaces with linear embeddings into that.
yes, but can you go to the slide? I think it was 39, I think. Yeah, 39.
What's the number?
So the next one.
Yeah.
Yeah, and here you do it for the vector space, right?
Yes, but if you think about the family of vector spaces,
Mm-hmm.
then you have to impose some regularity condition on this family, because not everything could be classified.
Mm-hmm.
So there is some hidden assumption in this construction of this family of vector spaces, forming a vector bundle, which is related somehow to flatness of this family. Okay?
Mm-hmm.
It corresponds to local triviality of a vector bundle, being a part of the definition of a vector bundle. Okay? This kind of regularity condition for classifiable family.
Okay.
So thinking about the vector bundle, you mean about the collection of fibers changing in a regular way along the base of this vector bundle.
Mhm.
So this
Yes.
is this algebraic family of vector space.
Okay. Thank you.
So the idea of this classification is that we are looking for an algebraic space, kind of space or scheme or something like this, parameterizing this algebraic object.
Okay.
May I continue answering the question? If you want to be even more concrete, think about just dimension one. Think about projective spaces, right? Special case of Grassmannians are projective spaces. Then these will be line bundles. And then I'm sure you remember a Mobius strip, right? When you're sleepy in the morning, you buckle up your belt, it's often a Mobius strip. And this is exactly, this is an example, right? This is a circle is RP1. And yes. Yeah. Yeah. Or if you want to go complex, you can think about CP1, which is a sphere. Then you can look at Hopf vibration, the Hopf line bundle, and that's a tautological line bundle. Then you can go to quaternions and so forth. And this is just projective space. Now, Grassmannians is that you allow your dimension to vary.
For more examples, you will see during the talk of lecture of Joachim Lielichiev. Okay, it will be continuing in a sense what I'm starting.
Anybody else? Go ahead, Adam.
I would like to ask about this Yoneda functor, since this Yoneda functor, goes into the category of sets. And
Yes.
at the end of your talk, you mentioned this whole business of topos theory. So are there any analogs of Yoneda functor in the context of toposes? Topoi?
There is a very ambitious program we are discussing about it by Jacob Lurie, even about so-called infinity topos, where the Yoneda lemma is proven in much more wider generality. Okay, so of course you can expand into higher categories. Because you are touching a very delicate point. Already you've seen that if you start speaking about, for instance, some set with structures, the totality of them can be organized into a category. But if you are speaking about the totality of categories, this could be organized in more than categories. Because if you remember, it's a category, there were objects, there were morphisms between them, which were functional, okay? But there were also higher morphisms, which are called natural transformations. So this is a tip of an iceberg, because you can continue this.
Yes, and sorry, could you remind me, this structure is called two category, or is it called B category?
It's a two category.
So there is a difference, yes? Which one is more natural, two category or bi category?
So two category is purely categorical. Typical bi categories is a rather algebraic version.
Mm-hmm. Okay, thank you.
For instance, bi categories, it's a kind of category which, for instance, could be used to formalize the language of so-called monoidal category. Because if besides the composition of morphisms, for instance, in the category of vector spaces, you can form, for instance, tensor products of vector space. These tensor products satisfy some compatibilities between this composition in this category of vector spaces, but also it's a kind of composition. Okay? So to speak about the relation between these two kinds of composition in one framework, people invented bicategory.
Okay, thank you.
And the point is, what you start asking is very important, because it's a natural tendency. If you start classifying objects of lower level, then you have to use structures of higher level. For classifying objects in the category, you have to use the structure of the whole category. You want to classify categories, you have to embed everything into the two category of categories. But you could try to classify also these objects of much bigger totality. Okay, and then you have to introduce higher and higher morphisms. Okay, and then everything ends up in the notion of so-called infinity category. Okay.
Okay,
And
thank you.
many classical results, modular problems, Yoneda lemma, go smoothly into this infinity situation.
Anybody else? Anybody from Zoom, perhaps? I don't see any raised hands. Okay, so Tomasz, let me ask you, can you give me some simple example of a functor that is not representable?
yes, sometimes it's even in the situation of the moduli problem. In the modular problem, fine moduli space sometimes is unrealistic. Okay. Even if you want to classify some algebraic or algebraic structures, it turns out that you cannot find, let's say, a scheme or a variety parametrizing this, being the fine moduli space for this problem. So this means that this moduli functor encoding this moduli problem is not representable. And for instance, if you want to classify object having some symmetries, some non-trivial automorphisms, okay, then instead of sets, you have to take functors taking values not in sets but in groupoids, and then you obtain some generalized kind of representation in objects which are called stacks, okay, which are even more generalized version of a space, moduli space. Okay? And it happens so even in the case when you want to classify Riemann surfaces. Okay? Because they can have some non-trivial automorphisms, and the result of these automorphisms is some additional action which has to be put into the structure of this groupoid when the modular functor takes values. And it is well known that resulting stacks cannot be represented by schemes, for instance. Very big business about exploring this exotic geometry of these generalized spaces produced, for instance, Gromov-Witten invariants. Okay? There are some invariants coming from this secondary kind of geometry of generalized moduli space, being by no means classical. So this means that the solution of this moduli problem in situations more complicated than the situation of vector spaces rarely produces representable functors. Moduli functors are not representable in principle.
So am I to understand that in our mathematical experience, representability of a functor is more of a rarity? It's a luxury that you frequently do not afford.
It's not so cheap. It's not so cheap.
Okay.
You have to pay price of more abstract constructions. But these stacks are not so bad because many things which are possible on usual spaces or schemes or varieties, like intersection theory, invariants, cohomological invariants, they are still possible. And this is not, it shouldn't be strange to you because you are an expert in non-commutative geometry. So non-commutative geometry is not about spaces. Spaces are not present in this theory. However, we can think about, for instance, sister algebras as a kind of generalized topological spaces. Okay? So this thinking about solutions to this classification problem as generalized kind of spaces was very fruitful.
Okay, thanks.
Sorry, I have one question related to this previous question. So you said that sometimes when we would like to classify objects with additional symmetries, this leads to stacks which cannot be represented as schemes. Yes, that's correct?
Yes.
Okay, so suppose that I know nothing about stacks. Is it somehow for me possible to recognize from the start whether this classification would be more elegant in terms of schemes, or is it somehow related to the kind of the groups of symmetries which we are interested in? let me be maybe more specific. If I have a space and a group acting on the space, usually one can consider as a set, at least, this classical orbit space, okay? And usually one sees what kind of action would lead to pathological spaces. For example, if the action is ergodic or something like that. And on the other extreme, proper actions are very mild in this context. So in your problem, is it somehow similar that from the start, it is already visible whether this classification answer to this question of classification would be easy or difficult?
It's very similar, because you can think about creating the quotient space for some action as a kind of constructing moduli space of orbits. Even classical spaces, if you think about space as a collection of points, so maybe I should give this as the first example. For instance, every algebraic variety is a fine moduli space of its points. So even thinking about space consisting of points it's like solving the moduli problem. What are you going to classify? You are going to classify points of this space, and this space is the fine moduli space of this classification problem, this moduli problem. Okay?
And there are no symmetries in this case of points.
Yes. So the second step, or second level of difficulty, goes when we think about actions, and then the classification of orbits instead of single points. Okay? It's much more complicated. So if you, for instance, you said about something about ergodic action, like for instance, the Kronecker foliation on a torus.
For example.
So the orbit is dense, but non-compact. Okay? Any kind of quotient, the quotient topology would be pathological. Only functions which are constant along the orbits of this action must be globally constant. Okay, so they couldn't be used as a model of functions on the quotient space. So in this situation, there is one solution to this difficulty. Instead of thinking about the quotient space, we could try to speak about the action itself as a presentation of some object which is called stack. Okay? And then, if you think about this as a generalized quotient, it turns out, surprisingly, that many things you can do with spaces can be done with this stacks, quotient stack. Okay? In non-commutative geometry, for instance, we have a similar construction. Instead of thinking about functions on the quotient, we can speak about something
about algebras.
Yes, cross-product algebra.
Yeah.
Which is another incarnation, algebraic incarnation of this stack. Okay. And it turns out that these cross products look for very good actions, like a free proper action, gives you something which is equivalent.
Morita, yes.
Morita equivalent. Equivalent with an honest quotient, but in the situation when this action is bad, it still makes sense as a stack. Okay? Or cross product with our algebra.
Okay.
So there are two parallel incarnations of the same idea in different branches.
Happy?
Yes, I'm happy very.
So let me ask one more question, but not to Tomek, to Bishan. Could you pass him the mic, please? Yeah, I'm sorry. Because you see what Vishan does, he participates in this beautiful classification program of sister algebras. And would you care to throw in just a few words of this classification program as an example that classifying using categories works?
Well, I will talk about this a little more on Thursday.
Yes.
But the functor that is involved there is based on something called K-theory. And actually, so Tomasz mentioned that this genus can be read off as a numerical piece of this category, this homology. And I will talk about something analogous. Well, this is something called a supernatural number that can be read off from this K-theory functor. So stay tuned.
Yeah, Thursday morning, right?
Yep.
Okay, so I think it's time to thank Tomasz for his beautiful presentation. Thank you so much. Let me stop recording.